Okay, in this lesson we'll be looking at probabilities. We're going to be looking at what we call disjoint and overlapping events. So we're going to be looking at multiple events, probabilities of more than one events, and there's different kinds of multiple events. We could have disjoint events and overlapping events. So we're going to talk about the differences between the two and how calculating the probabilities of these kind of events are done differently. We're also going to look at a technique where we can use the complement to find probabilities. Okay, let's start talking about disjoint and overlapping events first. Let's consider a Venn diagram. A Venn diagram shows the different outcomes that are possible for event A here. Anything inside the circle are outcomes for A. And then we have things that are outside of the event or the event A. That would be these outcomes outside of the circle. And we could also have another event B, and we have the dots inside this circle here, or this oval here, that represents outcomes within event B. So we have this terminology called the union, A union B, where this is it's a U. It looks like a U. A union B means the combination of all the different outcomes inside both events A and B. So I highlighted here all the different outcomes in the union of A and B. We also have this notion of intersection. An intersection would be just those outcomes that are common to both A and B. So these would be the three, in this case, three outcomes that are in the intersection of events A and B. We call, and here's another example of the union. It's slightly different in the sense that there's no overlap between the A and the B, the outcomes in A and B. This is the union. Everything within A combined with everything within B comprise the union of A and B. But in the case of the intersection, since there's nothing in common, the intersection of A and B is nothing. So we have names for these two types of things. We call the top type an overlapping type of events A and B, because there is overlap. There's these three here that overlap. And then in the bottom case here, we call these events A and B disjoint, meaning there are no intersection outcomes between the two. Okay, so let's look at the probability when events are disjoint. Again, when disjoint events have nothing in common between the two events. So the probability of A, the probability of event A would be the number of outcomes, all these dots within the circle A, divided by the total number of dots all within this total outcome space within the rectangle. The probability of B would be the number of outcomes or dots inside B divided by the total number of dots or outcomes inside the rectangle. So if we're looking at the union, the outcomes that are common or not common, the combination of all the dots within A or B, and we also think of union as kind of like I think of it as an OR as well. We can then add the number of dots within A plus the number of dots or outcomes within B and divide that by the total. And that's equal to the probability. So the probability of the union of A and B is the probability of A plus the probability of B. So here's an example. Suppose event A is choosing an ace from a standard deck of cards. Event B is choosing a king of diamonds from a deck of cards. And note, these two events are completely disjoint. There's no overlap. An ace, a king is not an ace, so there's no overlap. So the probability of event A is 4 divided by 52. 4 aces in a deck, 52 cards in the entire deck. The probability of event B happening is 1 king of diamonds, possible, divided by 52 total cards. So now, because A and B are disjoint, there's nothing common between the two, the probability of A union B, or let me say it another way, the probability of picking an ace from the deck of cards or a king of diamonds from the deck of cards is simply adding up the individual probabilities here. So we can add up 4 over 52 plus 1 over 52, and our probability then is 5 over 52. Now, in the case of overlapping events, it's different. Here's the case where it's overlapping, and we see these 3 outcomes, these 3 dots that are common to both events. Again, this is just the standard definition of the probability of A and the probability of B. But in this case, the union, the probability of the union of the two events is not, and that's the key thing, it's not equal to just adding up the number of dots or outcomes in A plus the number of outcomes in B divided by the total, because we're double counting 3 of these dots. If we add up all the dots in A here, and then we add up all the dots in B, we're double counting these 3 dots twice. And that happens to be, the 3 dots happen to be the intersection outcomes of A and B. So in this case, the probability of the union of A and B is not the probability of A and plus the probability of B. We have to subtract away the overcounting. So we subtract from it the probability of the intersection of A and B. And that's the key thing here. So let's look at an example. Again, let's take choosing an ace. As before, the probability of choosing an ace is 4 over 52. Choosing a heart. Let's call event B choosing a heart. And in this case, the probability of event B is 13 hearts divided by 52 cards. But in this case, let's think about the intersection between these two sets, A and B. There is an ace of hearts within the 4 aces, and there is an ace within all the different 13 heart cards. So again, specifically, the ace of hearts is the one card that is common between these two. So in that case, the probability of choosing that one ace, the intersection of A and B, is 1 over 52. So if we want to consider the union, what is the probability of choosing an ace or choosing a heart? That's what the union would be. Choosing an ace or choosing a heart. Well, we can add up the two probabilities, 4 over 52 plus 13 over 52 here, but then we need to subtract out this overcounting type of situation here. So we add and then we subtract away the overcounting, and we get 16 over 52, which can reduce down to 4/13. So we've looked at probability, how to calculate probability in the case of disjoint sets and overlapping events. Here's an example where we can just calculate, without even mentioning what A and B are about. Suppose we're given this kind of information. Probability of A is 0.25. Probability of B is 0.4. The probability of A or B, which we can consider as the union of A and B, is 0.6. Let's try to see if we can find the intersection of the probability of the intersection of A and B. So to do that, we write out this equation. That was the thing from the previous page. And then we can just replace. We have this part here, that's 0.6. Probability of A right here is 0.25. And then the probability of B would be 0.4. So we plug all those in, and now we solve for this unknown probability, just algebraically, and we come up with 0.05. So in this case, there is something in the intersection of this. So we know then, therefore, that this was A and B overlap in some ways because there is some sort of intersection between the two. Okay, you can practice on these problems. We're going to move on. Here's an idea about complements. The complement of an event, and we write it by writing event A with the bar on top, and we can actually speak it by saying A bar. They're all the outcomes that are not within A. So here, let's take an example where we define A to be all the cards that are hearts. In this case, A bar is all the cards that are not hearts, namely diamonds, clubs, or spades. How can we use this now? This concept is very powerful because we could say that the probability of event A happening is equal to 1 minus the probability of its complement happening. Or equivalently, we just algebraically move things around. The probability of the complement of A happening is 1 minus the probability of event A happening itself. Let's take an example. This is called the birthday paradox. If I have a room of 5 people, what is the probability that 2 or more people in that room share the same birthday? So this could be 2 people have the same birthday, or 3 people have the same, or 4 people have the same, or 5 people have the same. So we could try to calculate the probabilities of all these different things, but it's challenging. It's actually easier to consider the complement case, which is 1 minus the probability that none of the 5 share the same birthday. Let's see how we can figure this out. Let's figure out the probability that nobody shares the same birthday. Let's start off by just seeing how many different birthday combinations are there. If I have 5 different people, the first person could have 365 different birthdays, choices, times 365 times 365, because they could all have the same birthday. So it's possible that they all repeat and have the same birthdays. So there are 365 to the 5th power of different birthdays possible for those 5 people. Okay, so the numerator now, let's consider this. It's actually going to be this permutation here. Now, we're talking about the case when nobody shares the same birthday. So that means that the first person can be born any day of the year, but the next person cannot be born any day of the year, that he can only be born on 364 days of the year. And the following person only can be born on 363 days of the year, etc., 362, all down to 361. So then this is the way we'd write it over here. We could have written it with permutation language, 365, pick 5, same thing. But I just wrote it out like this. I think it's very convenient to write it out like that. Then we could multiply this out, and we get 21%. Let me back this up a little bit and clean it up. 2.7%. Okay. So there's one more problem for you to do on the bottom. You can give that a shot. Thank you.